Hi guys. So what we are going to study today is called as principal component analysis. Machine learning, as we know, is filled with a lot of algorithms. So why did we require another one to add on to the list? Well, let's picture this. You are running a pizza delivery company. The sales of your pizza are dependent on, let's say, so many attributes. The number of customers, the kind of toppings, the fast speed delivery, the cost of your pizzas, so on and so forth, the experience of the employees, loyal customers, and let's say about some 15-20 attributes. What happens is that when you try to understand what works the best for you, it becomes very hard to generate a pattern amongst all these data sets, and especially the number of attributes. So to solve the misery, we need to reduce the number of dimensions. In other technical terms, we can say the need of principal component analysis is to overcome the problem of overfitting. Now, for those of you who are not aware of what overfitting is, let me put it in very simple, oversimplified words. Let's say you plot two attributes here, okay, and you train a model. That model tries to reach maximum number of points in its training, while it's training. So you can say, in other words, that multiple number of attributes, you gave your model so many attributes that it actually got confused during training, and it tries to cover this point also, that point also, something like what most of us are trying to do with our life, trying to grab onto a lot of things, end up doing nothing. Jokes apart, that is the problem of overfitting. You can see I have tried to plot attribute say A and another attribute B, and these are all the points. So let's say that our model is represented on this line, and you can see that it's trying to somehow cover an entire set of points and data. So what happens is it is a little confused and there is a problem of overfitting. The solution to this is to do principal component analysis. Voila, you can decrease the number of attributes, and that somewhat reduces your problem of overfitting. Now, say there is salesman, there is cost, there is topping. How do you know that, okay, this attribute can be, the number of attributes dimension can be reduced without losing on much valuable information? Because if something is present in the data set, then it is relevant at some another level. So how much can you let go of? How many dimensions should you let go of? So I think by now it's to assume that you understand principal component analysis is sort of a tool which is used to overcome the problem of overfitting. And how does it do that? It decreases the number of dimensions. You can see it decreases the number of dimensions. Let's study how. So imagine that you have a data set. You can see this data set, I hope, and you can see that here are the data that these are tuples, and these are each attributes, let's say A, B, C. So as I was saying, for customer A, the attribute of buying a pizza based on, say, sales, the toppings, the cost, and so many factors. Let's say this is your data set. How do you change the way you view your problem? Yes, the answer lies in the word views. So if we look at our model in a different manner, bear with me, then we have a solution at reducing the number of dimensions. Now this might sound a lot of big words together in one sentence. So let's just come back to a simplified version. Focus on this graph. Right now, you, the person who's looking in the camera, is looking at this blackboard in a way that you see these points in 2 dimensions, and you see a line that's trying to accommodate all. Let's say you were supposed to stand in the view of the plane and view this from this angle. If you, let's say, saw this here, what would you see? You would essentially see all these points getting overlapped on this. A little bit of imagination is required. So you would see this happening. Now when this is happening, obviously a lot of points, to a person who is viewing like this, he might see a line like this. Okay. Now since you are getting to see a line over here where you are getting to see a two-dimensional aspect of these data sets, you get to see a one-dimensional mapping of the points. So what you can see is from 2D, you decreased the number of dimensions to one dimension, and this inevitably will result in a decreased complexity. So let's call this as principal component 1. So I think, let me summarize. There are so many points. Our model tries to touch each one of them. Hence, it bears with the problem of overfitting. Then, in order to reduce the number of dimensions, as we explained earlier, we try to view the same model from a different angle, and when we do that, we find that a lot of points which were initially probably not on the line seem to be mapped on the line along with these points again. That can be referred to as principal component 1. There are always two sides to a coin or multiple perspectives to a situation. So you can guess, if I would give you a second to guess if there's another way to look at this. Welcome treat. Yes. So let's say you were to view this from this point. Right now we are looking at it in a perpendicular angle. Now you were supposed to see it in a way that this is your line of sight. So if honestly the image that comes to your head is this one, a big kind of line circulated surrounded by these teeny tiny dots, then I'm afraid you need a little bit of more imaginative skills. Don't get offended. What you will be needing or viewing when you're thinking of a principal component analysis is a line which is perpendicular to this. Let's consider this plane. In this manner, all these points, this entire point gets mapped to this location, and all these points again get mapped onto this line. So again, the kind of image that we are observing will be this and not this. So it's safe to assume that this line, principal component 1, and this line, principal component 2, will be different from each other, hence the two different names. Now I ask you a trick question. Do you think there's another way you can view this so that you get a line over here? I'm afraid not. This is one of the most important points of principal component analysis. The number of principal components in a model will always be less than the number of attributes taken or equal to them. So in our case, since we were plotting between an attribute A, let's say speed of delivery, and attribute B, let's say cost of toppings, the maximum number of principal components that we could get was 1 and 2. Any other third thing is a naive approach to look at this. So this is a very important point that I want you guys to remember. Number of principal components will always be less than equal to the number of attributes for which the model has been trained. If there is a set of 3 attributes, say price of toppings, speed of delivery, and let's say customer's relation experience, based on those 3 components, a person buys pizza from your place, then you might end up having not 1, not 2, but 3 principal component lines. Now, let's say PC1 is this, PC2 is this, and for a dimension where you have more number of attributes that you're considering in your model while training, you will get PC4, PC5, PC6, and so on and so forth. Between these principal components lines, there will always be a confusion of which component gets the maximum priority. Which component is something that needs to be considered the most. To solve this problem, it's as simple as this. The order of importance is a representative of the number. So PC1 will be the highest and the most prioritized. PC1 will have the highest priority, something like your first rank comers. PC2 will have second most priority, PC3, so on and so forth. So this is something which will reflect and overcome the problem of overfitting. Another important observation I would like to conclude on before going is the fact that you should know all these principal component lines are essentially independent of each other. Again, jibber jabber big words. What do you mean by independent of each other? That means if you have a part of this line and you kind of want to take out its component, so you'll find a little bit of this is over here, component is here, this is little bit of it is along x-axis, little bit of it is along minus y-axis. So you can see there are two components in which it can be split. Therefore, if there's another line, let's say this one, okay, so then again when you kind of plot it, some component of that line will lie across this and some component of that line will lie across this for both the two lines, okay. So there will be some little amount of overlap between two lines which are not orthogonal to each other. That means if they are not at an angle of 90 degrees to each other, some part of these components will overlap. That is why it is a rule or an important observation that the number of principal components are less than equal to the attributes and they will always be orthogonal to each other. That is why if we took one view like this, we cannot take another view say at this angle. It has to be in the plane of the original view. So I hope overall you kind of get the idea of PCA. If you attempt numericals based on this, this will help you understand the concept better. Summing up in one line, principal component analysis is a technique which is essentially used to overcome the problem of overfitting. And how it does that is it basically reduces the number of attributes or the number of dimensions on which the model is being trained, and that way it decreases the complexity of the problem. Thank you.